This video is going to be a brief introduction into Kalman filters, what they are, why they're useful, and how to implement them. So what is a Kalman filter? A Kalman filter is a technique that we use to process sensor input in a robot or a self-driving car and combine it with predictions of its position and its velocity and things to maintain an accurate state estimation of where our robot is or how fast it's going, something like that. So let's imagine, we have like a robot moving along the ground here. It's got, two wheels, and it has, some X position, something like this. And we want to find out where our robot is. Well, we might take a GPS measurement. If we take a GPS measurement, the GPS might tell us, okay, here's, our best guess of where your robot is. But, there's an error bar associated with that, and so maybe it's somewhere in this confidence interval. And, confidence intervals for GPS can be several meters, so it's, there can be considerable error there, especially if you're, trying to avoid obstacles or things like that. And so a Kalman filter will give us the ability to use some math magic to give us a more precise estimate of where our robot is, other than just taking a measurement and trusting that and hoping for the best. Okay, so how do we implement a Kalman filter? Well, a Kalman filter comes in two steps. There is a prediction step and there's a measurement step. So first, let's talk about prediction. Okay, so we have our state vector, and we'll say this is x. And our state vector will consist of maybe our position in our x direction, position in our y direction, velocity in our x direction, velocity in our y direction, something like that. And then, this state estimation will also come with a certain amount of uncertainty, and so we could model that in what we'd call a covariance matrix P. And this is also going to be, if this is, we have four kind of state elements, then P will be a 4x4 matrix. Down the diagonal will be, the variance for position in X, and we'll have the variance for position in Y, variance for velocity in X, variance for velocity in Y, and in this case, we can assume that the rest of these, like the covariances, which would be everything that's not on that diagonal, we can assume those are zero, because we're going to assume that all of these are independent. And so we can fill in some zeros there. Let's think about how X evolves over time, or like how, one state estimation would depend on a previous state estimation. So we could say that, our state at time k would be equal to some kind of matrix, some kind of state transition matrix, times our, our original state matrix. So this would be like at, at k minus 1. And how can we figure out what goes in here? Well, we can think, okay, so our position in the x direction is going to be our initial position plus velocity times some kind of delta t, right? And same thing for y. So we could say that, okay, so then if I multiply it by a matrix that looks like this, then that should give me, my new position x estimate at, the next time. And same thing for y, I could do it like this, and then that would give me, my new y, and then we're going to assume constant velocity for these, so we'll just say like vx and vy don't change. So then vx will just depend on vx, and vy will just depend on vy. So this matrix right here is our state transition matrix, and we're going to call that fk. And finally, we're going to have one last matrix we're going to call Q that's going to model our process noise for this. It's a bit complicated to write down, but it's not that complicated to understand. It's also going to be a 4x4 matrix, and it's going to be based on an acceleration noise term. So if I just write these down, I'll explain as I go. Right, so we have this, and then times a, which we're going to say is kind of our maximum acceleration. Think of this as a as, you know, the acceleration it might experience getting buffeted about in the wind or shaken around or something like that. So we're introducing some kind of noise into our velocity. And I'll have 0, and then delta t cubed over 2 times a, and then another 0, and I'll close this off. We'll have a 0 here, and we'll have delta t fourth over 3 times a, and 0, and delta t cubed over 2 times a, and delta t cubed over 2 times a, and 0, and delta t squared, and 0, and then we have this, and 2 times a, oh, that should have an a next to it, and this should be 0, and this should be delta t squared a. And I'm also assuming here that this acceleration noise is going to be the same in the x and y direction. So I'm using kind of the same constant for this, just for simplicity's sake. So once we've got these pieces, you know, well defined, then actually the prediction step is pretty simple. We can say that, you know, our state at say time k, right, that we're trying to estimate, it's going to be f sub k times x k minus 1, right? So this is our state transition matrix multiplied by our previous state. It's pretty simple. And then our covariance matrix at time k is going to be equal to, okay, well, it's going to be f k times p times f, the transpose of that, and then plus that process noise. So this right here is our prediction step. That's pretty simple, right? That all we have to do is, you know, plug these in once we have them to predict what, like, both the next state would be, and both what the noise, or the uncertainty, I should say, behind that state estimation. Now that we have our prediction step down, let's move on to measurement. So I'm going to clear this, and we'll talk about how we incorporate a sensor measurement into our Kalman filter. So sensor measurement, we would say, is going to be, let's say in this case we have a LiDAR, right? So this just measures like the position in the x and y direction of something out in the field or whatever. It doesn't measure velocity, right? So we're going to have a 2x1 matrix. So a LiDAR is only going to take a measurement for the position in x and for the position in y, right? It's not going to take any velocity measurements. So, you know, if we have a measurement matrix, say, we'll call that z, and that's just going to be p sub x and p sub y. But I want to be able to compare this with, you know, what my state is to see, like, if, what the difference is between the two. And so I need to convert what my state matrix is, or my state vector, into something of the same form so we can see the difference. And so I'm also going to have a matrix H. I'm going to write this out and then explain it. In this case, it would look something like this, where you can tell if I multiply this, like if I wrote in, you know, my state matrix, my state vector here, h times, you know, and this is x, h times x is going to give me something that looks like p. It's going to be the same 2x1 matrix where we're just recording the px and py. So that's what we want. And then one final thing is we're going to have a matrix for the measurement noise. And so that's going to be, the variance for position in X and variance for position in Y. And we're going to assume, again, zero covariance right here. So that's our R matrix. And this is the noise in our LiDAR measurement. So once we have all of these defined, then it's a really straightforward way to update our state. So we're going to calculate the difference between our measurement and, I guess, what we would predict our measurement to be. So that would be z minus hx. And then we're going to calculate some other matrices, and we'll just go through these, because really it's just you just kind of have to do it once you have it. Sorry, I miswrote that. Plus R, so that's our S matrix. Once we have S, then we can calculate what's called our Kalman gain. And so that's going to be P times H transpose times S inverse. And so once we have these matrices, S and K, then we can do our state update. And so, my X sub K now is going to be my X sub K minus 1 plus that Kalman gain times Y times the difference in those two, the measurement and what I would predict that measurement to be. And my new covariance matrix is going to be I minus K times H in parentheses times my old P. This is PK, and this would be PK minus 1. And I is going to be an identity matrix, right? So this is, it's going to be a 4x4 identity. So this is my my measurement step now, that I had a previous estimate of where my robot was or something like that, and then I took in a measurement, and instead of just taking the measurement's word for it, I can use some of that prior information to help me, to give me a little bit more accurate or more precise measurement and a better picture of what my uncertainty is there. And then once we have these two steps, we can continually do these each time we take a measurement, so that we can constantly update the state of our robot. Right. So once we have these steps, say our robot's here, and it's cruising along. Every time a measurement comes in now, the first thing we're going to do is we're going to predict from what we know the state is, where it's going to be since our last measurement. So maybe we took a measurement over here, but then we've been moving for a little while, and then we get another measurement, and it's right here, and we'll say that I'll erase that other one, but we'll say that the error bar for that is this, and then we would also get some some measurement that says maybe it's here, and that has a certain error with it. But by combining these steps, we'll actually get something that is a lot more precise. And that's the cool thing about Kalman filters, is that we aren't just relying on our sensors to measure, but we actually use other information to give us a more precise measurement and a more precise estimate of where our robot is, what the state of our robot is.